For this example, we have a long straight wire carrying a current of 14 amps flowing in this direction. Next to the wire is a square loop with sides 1 meter long. The loop carries a current of 2.5 amps flowing this way. Calculate the net force acting on the loop due to the 14 amp wire. So let's think about what's actually happening here in this problem. This wire is creating a magnetic field. That magnetic field makes big circles around the wire. The direction of that magnetic field, here where the loop is something we can find with our right-hand rule. So remember, it's big circles around our wire. So if this is our wire, our magnetic field is big circles like this. I'm going to have to use our right-hand rule to find the direction of the magnetic field right here at this point. So we put our thumb with our current, and then we use our right-hand rule to figure it out. Sorry, I'm just having issues with my stand tipping over. Some days life is like that. Okay, got it propped up a little bit. Sorry to be so disruptive. So where was I? Yes, we're trying to find the direction of the magnetic field at the loop. So our thumb comes this way. Our magnetic field is going to be into the page right here. So our wire looks like this. The magnetic field makes big circles. We want the direction of the field right here. We see that our knuckles are going down into the page. So we can draw that if we wish. The magnetic field here, into the page, into the page. Gets a little weaker as we move out, so we might pull those X's further apart. Okay, so this loop is sitting in a magnetic field that points into the page. If we want to do the net force, we know we have to use force equals IL cross B. And the B is the B that comes from this wire. So the loop has 4 bits. It's got the upper bit, the lower bit, and these side bits. Let's talk about the side bits first. This side bit has a current that flows up. It's sitting in a field that points in. So the current is up, the field is in, the force is to the left. This one has a current that comes down, the field is in. Use our right-hand rule to see that the force is to the right. These two things are symmetric. The forces are equal and opposite, so the net force due to each of these two lengths is going to be 0. So we only have to deal with the force coming from the top and the bottom bit. So let's deal with the upper bit first. So what's the force here on the upper bit? First, let's figure out the magnetic field. So the magnetic field at the upper bit of the loop is equal to mu naught times the current in the wire. Remember, the wire is the thing making the magnetic field, divided by 2 times pi times the distance between the upper part of the loop and the wire. Okay, so there's everything we have. The direction is into the page. So if I put my x, y, z like this, that is going to be in the negative k hat direction. Or into the page, either is fine. So I've got minus 4 pi times 10 to the minus 7 Teslas meters over amps times my current of my wire, 14 amps, divided by 2 times pi. I see that this distance is 1.2 meters, this distance is 1 meter, so the distance for my upper part of the wire is 1.2 minus 1 equals 0.2 meters. Put all this through the calculator and we should get 1.40 times 10 to the minus 5 Teslas in the negative k hat direction or into the page. So that's the magnetic field at the upper wire. Let's go ahead and find the force at the upper wire. Well, we know force is IL cross B. We can also use our right-hand rule to find the direction. I'm just going to twist my paper here. This helps me cheat. So I've got I goes this way. That's my thumb. B is into the page. And then my force is my extended middle finger. It points up. So I could do my cross product, or I could do magnitude and direction with my right-hand rule. I think I'm going to go right-hand rule. So my force on my upper part of my loop points this way. Force for the upper part. Force for the upper part has a magnitude of I of the loop times the length of the loop from here to here, that's 1 meter, times the magnetic field at the upper portion of the wire times the sine of the angle between the current and the field, that's just 90 degrees. So I've got 2.50 amps times 1.00 meters times 1.4 times 10 to the minus 5 teslas. Remember, these are all magnitudes right here. So my force on the upper part of the loop is 3.5 times 10 to the minus 5 newtons, J hat, or up. So it points up. Okay, let's do our force on the lower part of the loop next. On my lower part of the loop, the magnetic field is still into the page. Let's find the magnitude. B of the lower part equals mu naught times I of the wire. Remember, it's the wire that makes the magnetic field here. 2 pi times R of the lower equals, for our direction of that magnetic field, it is going to be into the page because we've drawn that. So mu naught is 4 pi times 10 to the minus 7 Tesla meters over amps times my current in the wire, 14 amps, divided by 2 times pi. The distance between the wire and the lower bit of the loop are right here, RL. We see that from our picture. That's just 1.2 meters. Put that through the calculator, and we get B on the lower part of the loop is 2.33 times 10 to the minus 6 teslas, points into the page, so we can give that a negative K hat, or right into the page. Those are equivalent. For our force on the bottom part of the loop, F lower, we can do IL cross B, or we can use our magnitude and direction again. I think I'll go that way. So if I want to do magnitude and direction, I want to use my right-hand rule. I'm twisting the paper because it's easier than twisting my hand. My current goes this way. My field is into the page. My force is this way. So there's our magnetic force on the lower part of the loop. F lower. So we see that that points down or in the negative J direction. Let's go ahead and figure that out. We've got I of the loop times the length of the lower part times the magnetic field it's sitting in. So that's 22.5 amps times 1 meter times 2.33 times 10 to the minus 6 teslas. Dropped my sign 90. Sorry, I'll just stick that back in. So my force on the lower part of the loop then is equal to 5.83 times 10 to the minus 6 newtons. It points down, so that's negative J hat. To find my net force then, I just have to add those two things together. So the sum of the forces is the upper force plus the lower force. 3.5 times 10 to the minus 5 newtons J hat minus 5.83 times 10 to the minus 6 newtons J hat gives me 2.92 times 10 to the minus 5 newtons J hat. So our net force points up a little bit. With regards to the motion, that means if this loop were free to move, it would get pulled upwards towards the wire.